start the broadcast.
Yeah.
We can.
Parashkev is ready. I'll say 2 words and then go ahead. Good morning, everybody. The sun is rising behind the Swiss Alps, and I hope that you don't think that the best is coming at the end. On the opposite, we are starting with one of the highlights of the day. This is Professor Parashkev Nachev at the Institute of Neurology, UCL, who is, besides his bright side being a neurologist and taking care of patients, particularly with cerebrovascular disorders, also one of the icons in the field, particularly about methodology for distributed investigational and therapeutic devices. And I'm happy to introduce him, and the stage is yours, Parashkev.
Thank you very much for that generous introduction, and I'm delighted to be here, even if only digitally. So let me just share my slides so we can begin. So our subject is deep generative modeling of neurology. And what I would like to do is to keep the discussion at a fairly high conceptual level, because we will see that descending into the technicalities is actually not important at this stage. It's really the generalities that we need to establish. Perhaps we can begin by thinking about how it is we approach modeling conventionally, indeed how modeling has really always been done until very recently. We might take each individual, here represented by his or her brain, as being the average of the population with some noise added. This is really what conventional models tend to assume. And then we would typically seek a biomarker of some kind, for example, brain matter volume or total brain volume or something even more specific, but it would typically be a univariate measure or a low-dimensional multivariate measure that is supposedly characteristic of that patient. And again, it will be related to the population mean, where individual variability is essentially just noise. Now, is this an appropriate way to think about the biological, still less the brain? Well, let's imagine that instead of the brain, we're dealing with the face, something, a part of the body with which we're intuitively familiar. Here we have a reasonably homogeneous population. On the right, we have the average face of all cardinals of the Catholic Church. And you can see it's a distinctive face, but nonetheless, if we take an individual cardinal, chosen someone on the left here, you will see that the difference between the two is surely not merely noise. There is a structured form of departure of each individual from the population mean. So if we then begin to try to distinguish that individual by some biomarker, such as here interocular distance, we're obviously bound to fail. It's a relatively weakly individuating characteristic. Worse, when we start to perform what is currently known as evidence-based medicine, which essentially draws on populations in order to make decisions about individuals, we will get something of the following effect. Imagine that there is a problem with your target organ, here simulated with a particularly pleasant Photoshop filter. The way in which this is supposed to be managed within the rubric of evidence-based medicine is to take the same area from the average cardinal and transplant it over to the individual. Would that work very well if you're a plastic surgeon? Probably not. And yet this is what goes for state-of-the-art in medicine, even now. So what is the solution? Well, rather than seeking biomarkers, small numbers of features that may or may not identify an individual and his or her deviation from normality, what we can do is introduce more complex models. Machine learning, which of course everyone now is so preoccupied with. The problem is that conventional machine learning models, discriminative models that attempt to learn what is it specifically about a set of data that are associated with a particular outcome, what you get is simulated by this kind of schematic, where the model is paying attention to specific areas of the system that happen to be particularly discriminative. Let's imagine here, again, transplanting this to the face, that the features of interest are around the eyes. So what that model will do is to focus specifically on the eyes. And now instead of using the mean, it will be much richer. It will look at the decision neighborhood of people, individuals that are like this person. Now, what happens if there's some kind of anomaly? If the target organ is distorted in a way that means that the discriminative model is no longer familiar with the landmarks. Well, now, if it tries to look in the same region, here I speak of region in terms of space, but you need to think of this in terms of dimensional space, it will be misled. And so we no longer know what to do. So essentially, discriminative machine learning models, even if they're very sophisticated, tend to be unstable under distributional shift when something changes about the input that they're not familiar with. And there are other vulnerabilities. In particular, the specific kind of missingness that I really think ought to have its own term, clinical missingness. Clinicians amongst us know it very well. So data is often not there because you deliberately don't bother to collect it in the context of clinical care, but it's not always so. Sometimes it's merely accidental. There's a huge raft of reasons data might be missing. Where data is missing, of course, the model will may well end up being confused. It is also characteristic of medicine, certainly neurology, that there tends to be extreme class imbalance. Cases of interest to us tend to be relatively rare in comparisons to the ones that have a more straightforward outcome. And finally, we have the context of counterfactuals, in particular in the situation of trying to work out whether a particular treatment will work in an individual or not. Indeed, this is really what medicine is about, knowing what works for each patient. And here, what we have to do is to try to arrive at a conclusion about what the outcome might have been in a patient who has obviously never had the treatment before. So all of these vulnerabilities make discriminative models, even where they're high dimensional, even where they're much more sophisticated than the conventional approach, potentially vulnerable. So the question is, should we be worried about any of this? Is the brain indeed like that? Well, of course, this is a question that we can address empirically. We can look at brain data and start modeling it. Here, for example, by modifying the number of input features on one axis and then the number of training images on the other. This is 6,000 or so scans of patients with radiologically normal appearances, where we are attempting to predict the patient's age under those two different contexts, with, of course, different combinations in between. And the critical thing to appreciate here is that the error, which is on the z-axis, drops with numbers of input features. Unsurprising, the more characteristics we feed into the model, the better it is. But also look at the effect of the number of training images. Yes, this is a relatively inefficient model, but current models are not that much better. And you will see that we only really begin to approach minimum error for something as simple as age when we are feeding in thousands of images. Most neurological research is, of course, nearly in the hundreds, and so even something as simple as this will be far from optimal. And the picture is not all that dissimilar for attempting to discern effects of a brain. This is a skull strip brain, so of course it doesn't rely on anything other than the brain to make that discrimination. And you can see, again, it's sensitive to the degree of parametrization and the number of training images you feed in. Now, what happens if we actually confront the real, true complexity of neurology? Well, here we have a representation of 110,000 neurological reports, where we have extracted the characteristic features from each report and then embedded them in a two-dimensional space. So each dot here is an individual report, and its proximity or distance from any other is a reflection of how similar the reports are. So if you can think of this as being neuroradiology as refracted through the eyes of a neuroradiologist. And it's been labeled by the patient's age, which of course is not within the report. So it's something that emerges as a structure from the way in which these reports are organized. So you'll see that there's lots and lots and lots of clusters. Here, this broad swathe of all the individuals are people with dementia, the forms of neurodegenerative disease. The younger patients here are mostly inflammatory. Here we have a mixture into oncological and so on. But the key point is that there is a huge diversity of appearances. And the idea that any simple model can learn to internalize those is, of course, always going to be vulnerable. Even if we're to focus on a specific on a much more specific pathology. So here, for example, let's say we look at intracerebral hemorrhage, we see the same kind of pattern. So what I've got here is about 700 individual brain scans of patients with intracerebral hemorrhage. They're represented by maximum intensity projection laterally. So you can see little brains, and then the dots here show you where the hemorrhage is. And these, again, have been embedded in a space where the similarities and dissimilarities between scans are preserved. So here, these are all the cerebellar hemorrhages. Down here, we have deep hemorrhages. Ones at the front have penetrated into the ventricles and so on. Again, the key point is that there is a broad diversity of appearances, and modeling, as many people do, the lesion here as merely being represented by volume or any other simple characteristic is not compliant. So what are the consequences? Well, in the context of focal brain injury, for example, if we use univariate methods, so this isn't machine learning, this is conventional statistics where we take a particular region of the brain, single voxel in this simulation, and try to infer what might be the association with the underlying neural dependence, we end up with extraordinarily marked patterns of distortion. So you cannot properly associate damage to a specific region of the brain and outcome, unless you take into account the complex structure of lesions. But even when we deploy a more complex multivariate model, so the top result here is where we simulate a disorder that is provoked by damage to either BA44 or BA39. If we use a conventional univariate method, we end up with quite marked misinference. But even if you use a good discriminative model, something like a support vector machine, you end up with better separation, but it's still far from perfect. There are large swathes of the target areas that are not correctly identified as being associated. And when it comes to building predictive models, this will, of course, impair performance. Let's also think about what happens when discriminative models are used in a completely different way, when we attempt, as has become recently popular, to determine accelerated or decelerated aging in a patient with a disease, with a model that's been trained on normal individuals that have supposedly normal trajectory of aging. Well, let's take an algorithm of that kind and imagine that you were to give it this image that I'm showing you now of a patient with idiopathic intracranial hypertension. I bet, I haven't tried it, that it will say that this patient is much younger than he or she is, because of course it's bound to be driven by prominent features of age-related change, such as ventricular size. So here, the model is essentially totally misleading. And of course, why should it be anything other than misleading? It hasn't been trained on the data that you're showing it. So of course, how could it possibly know what to do? So what is the solution? Well, rather than focusing models on specific boundaries, we need to inform them by the underlying structure of all of the data. Where this a face, where we're dealing with a face rather than the brain, it means creating a representation of the face as a whole. And this is what we use generative models for. And in order for them to have the expressivity that we need for brains, we need them to be deep. Essentially, we need them to be constructed with deep neural networks. Now, rather than going into the technicalities of deep generative modeling, which are rapidly evolving anyway, maybe we should think a little bit about what we actually need in order to enable modeling of that kind. Well, it's no different from any other modeling. It needs data, algorithms, and compute, but the requirements on each of these three things are very different. First, when it comes to data, we're even more, it's even more important that we have huge scale, but in particular that our data is fully inclusive, that it doesn't just look at the particular cohorts that interest us. We have to be able to understand everything, because it is only then that we could plausibly make ourselves robust to distributional shifts. And of course, we need it to be richly parameterized. Here is an example from 1.3 million documents from neuropsychological reports that we're currently structuring at Queen Square, represented again with the same kind of dimensionality embedding technique. Handling 1 million documents is, of course, very difficult, but it is doable with the technologies currently at our disposal. And that is what we should be doing. We should be absorbing everything, extracting all the data we can, and structuring it, and then feeding it into the models. What about algorithms? Well, as I say, it's crucial that they have expressivity, which means they're capable, flexible enough to be able to absorb huge variations in underlying patterns. It's also helpful, partly because the structure of the brain itself suggests it, to use hierarchical models that decompose the appearances in a way that's hierarchically structured. Of course, it's critical, always critical, to strive for compactness, but of course, not the kind of excessive reductionism that we've seen in medicine previously. Here, for example, is a model that we're currently developing that can learn to create images of the brain of different ages. And so that now allows us to factor in the effect of age counterfactually in the context of a cohort where you do not have people of the appropriate age for the contrast that you're interested in. And then what about compute? Well, the only way to do this kind of work is to deploy an extraordinarily large number of processing units. I think certainly in the context of brain imaging, one would need probably about 500,000 or so worth of computer power, and in particular GPUs that have large memory and high bandwidth. Anything less than that is actually very difficult to produce results sufficiently rapidly. And the danger, of course, is that unless you have evaluated a particular architecture thoroughly, you have no way of knowing whether actually it could work. It may simply be that you haven't explored it hard enough. So in terms of actual realization, well, if we're demanding huge scale, then it's inevitable that we'll have to abandon the idea of using research data, or certainly not exclusively research data. The only way here is to use the large-scale, fully inclusive, low-quality data that comes from routine clinical care. And what's crucial here is that provided the model is right, that will actually be preferable to higher quality data that is of smaller scale and that is biased. So actually clinical data is ideal for this kind of modeling, and it's probably the best, but indeed the only approach. Now, in terms of algorithms, as I say, these are very rapidly evolving, and what we need to be comfortable with is the idea that they're constantly changing. We're not going to come up with one solution that then is going to be used for the next 10 years. This is not like SPM, where we can just learn the technique and forget about it. This is going to be an evolving domain that we need to keep open and continually evolving. And then in terms of compute, in terms of realizing it, as I say, what's crucial here is that we have sufficient computational power in order properly to evaluate an architecture. Here's an example from the work of my collaborators that's not deep learning, but I think it's quite illustrative. So it used to be thought that it would be impossible to extract any meaningful signal with ultrasound from the brain if it's enclosed by a skull. But what they recently showed is if you use full-wave inversion with a particularly complex algorithm, you can actually produce an image that is potentially comparable to an MRI. But this only becomes apparent once you put a supercomputer on a task for 2 weeks. Now you might say, well, that's clinically useless. Well, it is now, but of course, in a year or two time when the machines are fast enough, it means that we may well be able to image the brain with ultrasound at the bedside, which would be pretty amazing. So how do we justify the use of clinical data at huge scale, married to high-performance compute at exorbitant cost? How do we do it? Well, the best way seems to me to leverage other forms of utility, not clinical devices, but operational use, where the prediction from a model is used in order to enhance the operation of a hospital. Here is a very simple model that we recently published on predicting who is going to attend or not attend an imaging appointment. that uses more or less the same kind of machinery that we use in building our clinical models, but now applies it to a very different question. Is the patient going to turn up or not? And of course, the hospital finds that very useful because it allows it to calibrate its reminding tools in such a way as to maximize attendance. This is obviously a very simple example. Many more complex examples can be given. But if one can justify this kind of work operationally, that then means that it's much easier to introduce within hospital care. One then gets immediate benefits in advance of the very long and onerous regulatory process that governs clinical devices. And it means that we can produce benefit, produce patient impact straight away, or at least much more quickly than usual. So in summary, what we need is a fairly comprehensive digital infrastructure that's embedded within hospitals, that is powered by supercomputers, that is aligned with operational objectives of each hospital, and that inevitably will be assisted by enterprise. But I should emphasize this cannot be delivered by enterprise. There is no company on earth currently that can do this. This has to arise at the intersection between enterprise, hospitals, and academics, because all of it is so new, because all of it requires so much innovation. And of course, this needs to be massive, it needs to be large scale, otherwise it's not going to work. Now, I'll briefly go over some objections that are naturally raised whenever one brings complexity of this kind into the question of modeling the brain, or indeed any part of medicine. It's natural to say, well, hang on, but biological causality has to be simple. It has to be elegant underneath. There has to be a biological E equals MC squared. Well, no, it doesn't have to be. By contrast, biology actually has to be complex in order to give itself flexibility. And let's not forget that these deep learning architectures that we're now using are borrowed conceptually from what is actually observed in the brain. So if they're complex, well, the brain is a lot more complex still. It's also tempting to insist that biological causality must be easily generalizable. So there must be general principles here that we can ascertain in a cohort and then generalize to all else. Well, no. When you think about it, the information content of the brain, even if it were to be modeled as something incredibly simple, essentially as if it were a set of binary units, is still massively larger than the maximal genomic information content, as measured by the possibilities of base pairs in the whole of the genome. The discrepancy is huge here, represented in terms of the areas of this circle and that dot. And so the brain has to find a solution that, of course, cannot be drawn from the genome. It has to come from outside. And it has no problem with using something that's stochastic. It does not care whether or not the solution that it's arrived at in any particular case is an overfit, because generalization is not part of its mission. And finally, we like to insist that the biological models we use have to be intelligible. Well, again, biology requires no light. It doesn't care whether or not we can understand what it does. It merely needs to work. What should be more important for us is the ability to achieve the necessary predictive power in order to give the best possible treatment for the individual patient in front of us. And that is, I think, what we should end on, what medicine is and has always been about, which is an interaction between a clinician and an individual patient. It's all about how we can get as close as we can to what the optimal care for a specific individual is. And if we use information from populations, which is the only possible source, then we must apply models that allow us to descend to the individual level based on intelligence that we can draw from the population as a whole. Thank you very much. I will stop there.
Thank you very much, Parashkev. As you know, in our format, we'll be having questions and answer panel afterwards, and therefore we'll switch immediately to the next speaker, to Muriel Boschud. Thank you very much, and tune in a few seconds and talk to Parashkev and Muriel and me and Jean-Marie Anoni in 1 hour.